Sorry, I'm back. Sorry. They took light. Remember, I'm used to a broadband. I didn't notice that they took light. So the thing went away. I will have quickly connect with my Wi-Fi, my phone Wi-Fi. So I just quickly did that now. Sorry for that. Hope everybody is hearing me.
Yes,
Please,
sir. Thank
Yes,
you.
sir.
thank you. Okay,
Yes, sir.
thank
You're
you.
back.
Sorry, I'm back. They took the light here and the Wi-Fi went away. The broadband went away. Okay, now what I was saying. So for you to know the expected value for May employment in that first cell now. So the number among the total that I employ, 185, the number that should be accrued to the May should be proportional to the contribution of the May to the total. The May contribute 130 out of 300. So that 185 multiplied by that 130 over 300 should be the number contributed by the May. That would be 80.17. The same thing for female. Since female constitute 170 out of 300. So 170 times 300 of 185 should be the number for the female. You can see now. So normally it should have been 80.17 for the male and 104.83 for female. Instead of, and the two will still add up to 185. Instead of 1995 we have. So now actually male should have been 80 of them. One female should be 105 of them before you can say that yes, there's no the proportion of male and female that they employ are the same. If you try to convert this thing now, this 80.17 and 104.83 to percentage now, 80.17 over 130 expressed as percentage, 104.83 over 170, you see the proportion will be the same. The same thing is applicable to the non-employed because the total that are not employed is 115. So the number that of female or male that are not employed should be proportional to the total contribution of male to the total, the contribution of male to the total. So that's why we now have 130 over 300 of that 115 for the male that are not employed. The same thing for the female that are not employed. 170 over 130 times 115. So it give you for the male 49.83, female 65.17. So if actually the number that are not employed are the same, the proportion of male and female, we expect 50 male employed and not employed rather, and 65 female not employed, not 40 and 75 we have. So if you do 9.83 over 130 and 65.17 over 170, the proportion will be the same. So that is why we call it this value you see we just calculated. They are the expected value, the value that we expect if there's no difference, the proportion of employed or not employed among male and female. Can you see the logic now? That's the logic behind. But sometimes for people to quickly grab and understand, the people use mnemonic. They say row total for each of the cell. Now, if you want to calculate the expected value for each of the cell, just say row total times column total over grand total. That is the cell may employ now. That first says now, what is the row total? Row total, that is the total along the row, that row where that cell belongs to is 130. The column total is 185. The grand total is 300. So 130 times 185 divided by 300. Is it not the same thing? It's the same thing as 130 over 300 times 185. Can you see 130 row total, 185 column total? That is, can you see there? Divided by grand total, which is this other one. Just a minute. Is just 1 minute. What is this one? Okay. Sorry, the one we did that is done is got converted. I'm try is blocking me. I'm trying to remove before instead of logging out. Okay, I have to stop sharing. So let me share again. Yes. Can you see now? So if anybody has, you try to calculate the percentage of the percentage of women of male and female employed, not employed from the expected value, you see that it's the same. The percentage of male is not employed is the same thing as female not employed. The percentage of male employed is the same thing as female employed. That's just it. So that's the logic between the expected value. Now, the chi-square now, I've already told us it's about division. Okay, look at it. If you try to look at the formula now, look at what we did. For each of these cell now, that's what we calculate. For each, look at the calculation. 90 minus 80.166. I tried to not to approximate it too much. So you see, observe for the first cell minus expected. You square over expected for that cell. The same thing is the second observe, which is 40 minus expected 49.83 square over expected. The same thing you do for all the four sets you add together, it gives you the chi-square. Now, you will see something. Look at each of the observed value and expected value when you try to minus them. 90 minus 80 point something, it gives you positive because 90 is greater than 80. 40 minus 49, it will give you negative because 49 is greater than 40. If we didn't look at it, the second row, you see that before you do the squaring, you see it gives you minus 9.83. The other one, 95 minus 0104, will give you negative also. While 75 minus 65 will give you positive. You see, if you look at it very well, without squaring it, you discover that the negative will cancel the positive. The value, the negative will cancel the positive. So the logic behind it is squaring is to remove that. If you remember when we were talking of summarization of quantitative when we want to calculate variance, you remember when you remove expected value, which is mean. I already told you mean is an expected value. You remove from each value those values that are less than the mean. It will give you, when you remove mean, it will give you negative. The ones that are equal to the mean, when you remove mean, it gives you 0. The ones that are greater than the mean, when you remove the mean, it gives you positive. If you try to write them together, you give 0, you get 0 because mean is in the middle. So as much that are less than the mean are higher than the mean. At the end of the day, if you add it, it will give you 0. That's why intelligent people say we cannot do this because if you get 0, you cannot go further. They now square it. It's the same logic here. You square the observed minus expected before you divide by the expected. So what you are looking at here, you are not looking at you like more or neglecting the sign. You want to eliminate that negative sign so that it will not cancel. You end up getting 0. That's why the square. That means logic behind square. And this logic go with all the statistics. If you are doing ANOVA, you are doing regression, you see mean square. You see something square, mean square, sum of square. Sum of square is a logic which you need to understand from. You see the same logic. So observe and not expected. So if you look at it, then you are looking at the difference. You are looking at the difference between when this value is what you have and when there's no difference between the 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 two when there's no difference. If there's no difference, if all value are the same, there's no difference between, for example, in this one, male and female, it's expected value you get. Observed value is what you are seeing, observed different now. So you are trying to now use that difference as the numerator. Then the expected value, which is in the state where there's no difference, which serve as the natural variability you observe, will serve as denominator. Can you see now? That is logic. But this logic is easier when treated. That was where when I was giving lecture on assumption around hypothesis test, I used t-test because it's easiest. But this other one, they are not as easy as t-test, but it's the same logic. So if you look at it now, we now have a chi-square is 5.55269. You should approximate to 5.553. Now, I told us the other time when we discussed chi-square distribution, I said that what is the critical value? The area under the, the area under the graph of chi-square based on the degree of freedom. This one, how many degree of freedom? Who can tell me now? Because we are discussing. What is the degree of freedom for this scenario now? This 2 by 2 table. What is the degree of freedom? We have talked about it.
1.
What do you say?
It's 3. 2 minus 1. Huh?
Is it 3? Is it 1?
Minus 1. 1.
It's 1. The degree of freedom is 1. We already said that the number of row minus 1 times the number of column minus 1. 1 minus 1 times 1 and minus 1. I give you 1 times 1. You've forgotten the logic. That row minus 1 times column minus 1, number of row minus 1 times number of column minus 1 is like a mnemonics. I already told you, if you want to get the degree of freedom, we have already told you the total are fees 130, 170, 185, 115, 300, all of them are around their fees. So if you change, you can only, if just you put all the total around and the 4 sets that are empty, if you have to put the value, you can decide to put value. It's only one cell you can put. You can decide. You can say this cell one of the cell, that for example, you can even choose the first one, a May employee, which is 9. You can say it's 80. It doesn't mean anything. If you put, it can vary. Instead of that, it can be 80. If it's 80, automatically this other one will be 50. They are not employed because the total for me is 130. So if the main employee is 80, that's what the main not employed will be 50. And if the main employee is 80, main employee is 80, because the total employee is 185. So the female employee will be 105. And of course, if this one is 105, what will be here? It will be 65. Can you see? So you can only change, you can only vary one because automatically one should vary one set. So this expected the degree of freedom is the number of entities that can vary on its own. It's only one that can vary here now because the rest are fees. But if you are having 6 sets now, 2 will vary, the degree of freedom will be 2. But the logic behind row minus 1 times column minus 1 is more like a mnemonics for you to remember, but this is the logic behind it. So the degree of freedom is 1. And if you go and look at the statistical table, which I showed us the other time, under the degree, maybe I should go back there. I think, yes, look at it. It's not even far. Look at the statistical table. Look at this one at the top right corner. You will see that the area under this is a chi-square degree of freedom 1. The shape depends on the degree of freedom. This chi-square degree of freedom 1 in this situation now. And you will see that the area under the graph is 100%, which is 1. But to one side, that will be 95%. Since our level of significance we are showing, most of that is 5%. So it means that the area under the graph, you divide into 2. One side will be 95%. The remaining, the significant side is 5%. The 95% side is the level of confidence. while the 5% is the level of significance. So along this column with this graph with the degree of freedom 1, if you are measuring the value of chi-square from 0 horizontally, where you have this graph divided into 95 and 5% is 3.84. The chi-square is 3.84. That is the critical value for the chi-square degree of freedom 1. This one below now is for degree of freedom 6. The critical value that will separate if the shape of chi-square degree of freedom 6, and at the point along this, if you are moving horizontally right, the value of chi-square that corresponds with the point at which you have 95% area of the graph, then 5% area of the graph on the left is 12.23. That is the critical value of chi-square for degree of freedom 6. I think it's very clear now. So it's the same thing that I show here. You can actually show it either in a graph or the table. For this table now, if you look at it physically, degree of freedom 1, so the green area is the level of confidence, the blue area is the level of significance. So our confidence level, we are talking on 95%. You know, confidence level and significance level add up to 100%. They share the area. The total area is 100%, which is 1. So if you look at it, you now go to where the confidence is 0.95, which is 95%. And the corresponding p-value is 0.05. That is the level of significance we have chosen. And what is for the degree of freedom 1, what is the critical value of chi-square is 3.841. Can you see? So that's why in your calculation, when you must be able to know before you can conclude, you must know what is the what do I call it? What is the degree of freedom, and what is the critical value for chi-square? The degree of freedom 1 at the level of significance 0.05, which is 5%, or at 95%, it means the same 95% level of confidence. So the value is 3.841. But we have now calculated a value which is even far ahead. 5.553 is far greater than 3.841. That is why we know that the corresponding p-value, which is the probability that the difference we have observed before is due to chance, will be less than 0.05, because it is 3.84 that corresponds with the 0.05. So if we now have value that is higher than 3.55 for our chi-square, the corresponding p-value will be less than 0.05 because they move in opposite direction. But all these things, those are were the thinking in those days. But now, I'm just emphasizing so that you know the logic. If you run with SPSS, it will give you the chi-square, give you the p-value straight without wasting time. Any question here? So let's now continue our day discussion. If there's no question.
Sorry, sir. The last slide, the slide you just.
Okay.
So you're saying that any value that is less than the level of significance.
Any value that is for you, any value, if you calculate chi-square now, that is less than 3.841, because 3.841 is the critical value for chi-square degree of freedom 1 at 0.05 level of significance. The 3.84, anything you calculate less than 3.8, that shows that the corresponding p-value will be greater than 0.05. There is no significant difference. You will not tell that there's no significant difference between the male and female that are employed. But in our conclusion, and because our value is far higher than 3.841, so you cannot say there's no significant difference. So there's a statistically significant difference in the employment status of male and female. It's different.
I don't know. Okay. Yes, maybe I'm the one mixing it up. I don't know. I think maybe the student knowledge. I don't know where I've always maybe something else that we're talking about then. And when you say something is less than a particular value, then it's significant, statistically significant. If it's more than that value, it's not statistically significant.
That's the
Am I-
p-value. That is the p-value. That is the p-value. That is the p-value. The one they are talking is p-value. It's the same
Oh,
thing.
okay.
I said that the p-value and the statistic, they move in opposite direction.
Oh,
So
okay.
for the p-value to be less than 0.05,
It's
the
statistically
statistic, yeah, for it to be, yeah, the statistic
significant.
will
Okay.
be higher than the critical value.
Okay. Okay.
So that's what has happened here now. The
Okay.
chi-square we calculated is 5.553, which is higher than the
Okay.
critical value of 3.841.
Okay. So you're saying this 5.53 that the p-value is going to be higher than it's going to
The
be less than
p-value will be less than
less
0.05.
than 0.05.
Because
Okay, okay,
this
that's what
value is
I'm
higher
mixing
than the
up.
critical value, the p-value will be less than the level of significance.
Yes, that's where my because I know that my root something what I know that something when it's less than that, that's when it's statistical. So I was now wondering why this one is higher and statistical. I understand it. So this one is level of this one is critical value. The other one is p value.
P-value.
Okay, all right,
Yeah.
thank you.
But without, in those days, without computer, you cannot calculate p-value. You
Yes.
can calculate the statistic. That's why we cannot see p-value here now. As per pay we have calculated, we cannot calculate p-value. You can only calculate this critical value. We can only calculate the chi-square value. We are now
Okay.
going and use statistical table to know the critical value.
Okay.
So if the value you have calculated is exactly 3.84y, exactly the critical value, that shows that your p-value is 0.05 exactly.
5. Yes. Yes.
But if it
Okay.
is higher than this critical value, your
3.84.
p-value will be less than 0.05. If it is less than what you calculated is less than this critical value, your p-value will be
It is
greater than 0.
higher than 0.05. Okay. All right.
And it is
Thank
when
you.
the p-value is less than 0.05 or equal to it that will be.
Statistically significant.
Another way, it is when the value you have statistic you calculated is equal to or higher than the critical value that it will be statistically significant.
Okay.
Does it make sense now?
Thank you.
And now you know that this p-value is the end point of all hypothesis tests. So the p-value is the same for all of them, but the different statistics like for example, t-test, ANOVA, many, all of them, they have their statistics. But it's the same p-value we use to judge them. So the end point of each statistic is p-value. Of each hypothesis test is the p-value. The end point you use to judge is the p-value.
Okay.
But that
Okay.
p-value, you cannot calculate it. But the computer can calculate it. So that is why by the time you run with SPSS or any software now, it will give you the calculated value and even give you the p-value. And you see with your eyes, if it is less than or equal to 0.05, you have set.
Okay. All right.
Yes.
Okay.
And that's why you don't need the statistical table. The computer has made it, you don't need statistical table.
Only.
But all this one is just for us to know the logic behind it. So that
Okay.
sometimes also, if by time there's no memory about it, maybe people may not know the reason. It
Why?
just look like a crime work. Any other question?
All right.
So now this what do I call it? Chi-square. Yeah, okay. Let's talk about Yates correction. This Yates, we have calculated chi-square now, but we have used 2 by 2 example of 2 by 2 table. So when it is not 2 by 2, it's the same. If, for example, now there are 6 cells, it's just for us to calculate the chi-square for the 6 cells. 6 cells, we have degree of freedom of 2. So if for us to calculate the same way, so it's only the cell observed and expected will be in 6 places because there will be 1, 1, 1, 1, 1 for each of the cell. If it is a cell, the same. Of course, you cannot have 7 cells. You cannot have a number of cells because it's a cross tabulation. It has to be divisible by 2. 4 cells, 6 cells, 8 cells. You cannot have odd number of cells right now. So then let's talk about what is the logic behind what we call Yates correction. This yield correction is used to prevent overestimation of statistical significance for small data. Small data, what they mean by small data is, number one, the 2 by 2 table. Then the sample size is not much. So you may begin to see that the value in the each set may not be much. Unfortunately, it may tend to overcorrect. Typically used in chi-square analysis, 1 degree of freedom, that is 2 by 2 table. Expected frequency of less than 10 in at least one cell. When you have expected frequency less than 10 in at least one cell, those are the conditions that make people to use yield correction. Some statisticians argue that expected frequency lower than 5 should trigger the use of yield correction. Others argue that yield correction should be used in all 2 by 2 chi-square analysis. To me, I don't even believe that you don't bother with yield correction, because some people also have criticized it, that it has over. It was proposed by Professor Yates, and the logic behind it is this. So, what is the logic behind this continuity correction? The binomial distribution is discrete and can be represented by probability histogram. You know, the even chi-square is a continuous probability distribution on its own. Then is used for data that follow binomial distribution, categorical data. You know, categorical data follow binomial distribution. What do you mean by that? You know, binomial means 2 categories. So when we talk about categorical variable, anyone that there are only 2 categories is followed binomial distribution or dichotomous. So male, female, followed by binomial distribution. Sex is only 2 possible, either male or female, yes or no. Anything yes or no, there, not there. Alive, anything that the possible value of the article, the possible value is 1 out of the 2, only 2 possible value, it followed by binomial distribution. But if you look at it logically, everything that is categorical followed by binomial distribution. For example, when we say, now we say ethnicity, Hausa, Igbo, Yoruba, others, we have 4 categories most of the time when we do our research in Nigeria, especially in Lagos and Abuja. Now, you will see that there are 4 categories. It doesn't follow binomial distribution. But logically, if you look at it critically, it's actually following binomial distribution. You can say, okay, Hausa and others. You can collapse others and compare the proportion of Hausa with others. You can collapse others and say Igbos and others. You can collapse others and say Yoruba and others. All those ones they call that, you can collapse Igbo, Hausa, and Yoruba and say compare with others. Whichever way you can have 2 categories. That is the logic behind that. Categorical variable actually follow binomial distribution, because you can maneuver it for it to follow. So anything categorical follow binomial distribution. So to calculate exact binomial probability, the binomial formula is used for each value of x and result are added. So geometrically, this corresponds to adding the area of bar in probability histogram. But all this here, I wouldn't want to bother you so much, because it's not actually necessary. So don't let me bother you the nitty-gritty. Some of these things is for academic purpose. But the logic behind it is that what the Yates now did is that since the chi-square itself is a continuous probability distribution, but used for data that follow binomial distribution, he believed that when the number of cells is small, it doesn't bring the margin point between binomial and continuous is not smooth. So it has okay to bring in some element of continuity. You know, continuous distribution usually have decimal. You know, continuous probability distribution usually have decimal. So it's not whole number. So what he now did is that after you are saying observed and not expected, We now remove 0.5 minus 0.5 for all of them. When you calculate your this, look at it for each. It's the same thing we have calculated now. Look at it for that the one we have just solved about sex and employment. You look at it the same. But when we say observed minus expected, we also remove 0.5 for each of them before we square. And that removal is absolute. It doesn't have respect for the sign. For the sign. You know that if you say minus, if you say 5 minus 2 minus 1. 5 minus 2, it give you 3. Minus 1, it will still give you, what do I call it? It will give minus 1. It will give you 2. But if you say minus 5, or if you say 5 minus 7, it gives you minus 2. Minus 1, it has become minus 3. So that is real mathematics. But that particular thing is absolute value. So if we are doing the year correction now, if you say 5 minus 7, you know, it's 2 that is the difference. Minus 1, it will not remain 1. That is what they are doing here. You don't have respect for that minus, because if you have respect for that, it will have to be, it's absolutely different. So the difference between 5 and 7 is 2. So the difference between 2 and that 1 is 1. That's what you're looking at. But if you follow the sign, if you say 5 minus 7, it gives you minus 2. Minus 1, it gives you minus 3. What you now get is 3. So here you don't have respect for that sign. It's the absolute difference. It's just to reduce the difference between the observed and expected. Forget about the sign. That is what you do. At the end of the day, look at it across. Sorry. Look at it across. It will reduce it. So eventually what happens is that it will just reduce the value of the chi-square small. If you remember, without yield correction, we got 5.553. Now with yield correction, 5.002. So it's not too far. It's still significant. There's another way to do it, just some mathematical jargon. Yet, if you run this thing, it will give you all these things with expresses. But it's good if, for the people that are going for exam, do master, they still give you to solve. You need to know it. If they are not doing that, it's just for you to understand the logic. Then know how to use expresses. Now, the yield correction now, what some people use to their advantage. In this case, now both yield corrected and non-yield corrected chi-square, they are significant. So many people, they say, where's yield corrected? 2 by 2 table, yield corrected chi-square. So some people, if let's say this value is almost significant now, maybe the value is around the critical value, which is around 3.84. Maybe something like when you calculate your chi-square, it's just 3.84. Just escape. If you do the yield correction, it will be lower. It will be almost significant. That one, the no corrected one will be significant. The yield corrected one will not be significant. People will now show, no, which yield? You will now choose the one that is not yield corrected. But if both of them, like in this case now, they are far, far above the critical value. You know, okay, yield corrected, chi-square, you just put yield. You just use the advantage. But me, I don't even fancy it to be sincere. Now, that's about yield correction. So likelihood ratio chi-square. This one use logarithm instead of what we use. But eventually, it's an alternative way. So you use what we call log likelihood theory. Yeah, I don't want you to bother about that. If you solve it with it, it gives you, this is just it. You use log instead of, it will give you, can you see now? The value is a little bit higher, small. than the one you use Pearson to calculate. But it's just small. Most of the time, it does not, it will be, if it's corrected, if it is significant with chi-square Pearson, it will be significant with likelihood ratio chi-square. Can you see all of them? The Pearson chi-square for the same thing, 5.553, yield corrected 5.002, likelihood ratio chi-square 5.609. Is he talking about the same chi-square? So if you run with SPSS, I think, yes. If you want to do SPSS, the same thing, I run with SPSS. This is just a step because the same data, I have it in SPSS. If you run it, eventually, these are the steps. Eventually, it gives you the output like this. Look at the table below. You see Pearson chi-square 5.553, continuity correction, which is the Yates correction, 5.002, likelihood ratio chi-square 5.609. Fisher exact test, can you see 0.0? The Fisher exact test, I will talk about it. I think is here on my slide? Yes. Let me just say, we'll talk about it. The Fisher exact is not a statistic, but is p-value directly. Log linear association, those ones not useful. You know, computer is garbage in, garbage out. When we get to chi-square for trend, that linear by linear association is the same, is what is chi-square for trend. Is the way SPSS talk about chi-square for trend. That's what SPSS call linear by linear association. So it's not useful in this situation. You know, computer is garbage in, garbage out. It's you that know what you want. If let's say now we are looking at association between sex and outcome is maybe level of education, because sex can determine level of education. So the level of education is ordinal variable, no formal, primary, secondary, tertiary. Why the exposure variable? No. No, it's not in that situation. Let's say level of education and employment status. Yes, the level of education can determine employment status. So the exposure variable is ordinal, which is level of education. The outcome variable is dichotomous, which is employment status. Now we may want to know chi-square for trend. So this one will be useful. But as you put in calculate chi-square, computer will run for you because it doesn't know. The computer doesn't know if the data, which one is exposure or even if you know, it doesn't know if it's this. Though you can feed it there and say that this is ordinal or whatever, but garbage in, garbage out is computer. That one is not necessary here. Now I want us to look at this first table. So you see when we run the chi-square, you had liberty to know when you run with SPSS or software, you have liberty to know something. You have liberty not to bother yourself with information. It depends on what you click. It will give you an opportunity. We want to have you know the percentage along the row. Since we have already chosen our exposure variable along the row and our outcome variable along the column, so it makes sense you know the percentage along the exposure, which is along the row. So that thing I was asking you the other time, you will see that 90%, 90 over 130 is 69.2%. That is 69.2% of May were employed. 95 over 170 is 55.9%. 55.9% of May female are employed. From here, you know from observed value, you know that more male rather are employed than female. So we can swear show. I don't know if I show it here. No, I didn't show it. While running it, you can show expected value. The computer can give you expected value, but I didn't show it here. You can ask the computer to give you because it will give you observed value as you can see, but it can give you the expected value. So, but in examination, you can calculate the expected value, row total times column total divided by grand total. That's how to calculate the expected value in exam. So what is the expected value? Now, there are some other things we need to know. You will see this second table down. You see the expressions will give you some alert, and that's the alert. You see, the zero cell, the first row under the table, say is zero cell because it refers to A. That A is attached to the Pearson chi-square. You say it's zero cell is 0%. Half expected count less than 5. The minimum expected count is 49.83. If you look at the when we calculated the expected count the other time, the smallest one is for, I think it's for which one? It's for we may not employ 49.80. That's the smallest expected count, 49.83. Now, if you remember the lecture last week, I said that the condition for using chi-square, one of the conditions, the expected count should not be less than 5% in more than 20% of the cell. That is, the expected count should be at least 5% in up to 80% of the cell. When you now, so you can, that is 20% of the cell can have expected count less than 5. It's acceptable. 80% have expected count at least 5 is 5. Then we have up to 20% have expected count less than 5. But a situation where you now have more than 20% having expected count less than 5, chi-square is not valid. Now, this situation now will not be, look at this. If let's say there's one cell in this 2 by 2 table, because there are 4 cells here, that has expected count less than 5, the chi-square will not be valid. Because one cell here is 25%. There are 4 cells. 1 out of 4 is 25% of the total number of cells. 2 out of 4 is 50%. So 1 out of 4 is 25%. If you have, thank you, expected count less than 5 in 1 out of these 4 now, chi-square will not be valid. But if there are 6 cells, because 6 cells, in the situation when you have 2 by 3 table, you have 6 cells. 1 over 6 is around 60.7%. It's not up to 20%. So when you have expected count less than 5 in 1 of them, the chi-square will still be valid because that 1 out of 6 is not up to 20%. But if you now have expected count less than 5 in 2 of the 6 cells, 2 of the 6 cells will be around 33.3% of the total cell. It's already above 30%. So the expected value will not be, the chi-square will not be valid in those, in the, because we have expected count less than 5% in 2 cells out of 6. Then if it is 2 by 2 table, once you have 1, it's not valid. That's not only the condition. If you have, forget about the number of cells, if you have expected count less than 1 in any cell, chi-square is not valid. Once you have expected count less than 1 in any cell, chi-square will not be valid. That is why the people that did, the owner of the expresses, they employ statisticians. They gave them advice. So what they do, look at it. They will tell you the number of cells that has expected count less than 5 and give you the percentage in bracket. Here now, no cell. That's why they say 0%, 0 cell, 0 number of cells. There's no cell that have expected count less than 5. That's why they say 0. And if 0 means 0.0% also. Have expected count less than 5. They now say the minimum expected count is this. Is for them, that second statement is for them to know if there's any expected count that is less than 1. Can you see now? If there's any expected count that is less than 1, by the time they give you the minimum expected count, you'll be able to know if at all there's any expected count less than 1. Can you see? The first statement will give you the proportion of the expected count less than 5%, in less than 5 rather. While the second statement will give you clue whether there's any cell at all as expected, less than 1. Whichever of them come, chi-square, either both or any of them, chi-square is not valid. We now go to use Fisher exact. The Fisher exact, that's why when you are running your statistics, there is a place you click on that will allow you to calculate the Fisher exact also. When you are running chi-square, you go to put this Fisher exact here. Fisher exact is probability. Straight. I think there is a, yes, I think there is a place. I talked about it also before I came here. Fisher is, because I just came. Fisher exact. Yes, I think it's here. Fisher exact. That's how to permutate just one funny, you don't need factorial to calculate. The issue is that this one does not calculate. It calculates the p-value straight. It calculates p-value. That's the only situation you can calculate p-value. You cannot calculate p-value from those statistics. You won't know, but Fisher exact we calculate p-value directly. So those machines, the computer give it to you anyway. So if the expected value, any of those two things are violated, Fisher exact value is now used instead of chi-square. Any question? What is the time now? Well, in fact, chi-square, we have to be taking it dose by dose. I think we stop here, or else we will be confused. So next lecture, we'll talk about chi-square for trend. So if you can talk about the trend, chi-square for trend, and another one in next lecture. Maybe in the next two lectures, we'll finish with chi-square. It's a very important statistic. Any question?